Hello everyone, thank you for coming. Hopefully you are going to understand what I'm going to say, because my voice is, as you can probably hear, not very good because of sore throat. Anyway, actually I'm lucky that I can be here with you, because 2 months ago I got an injury, and 1 month ago when I was asked to do something like this, I was not sure if I'm going to be able to do it. Did any one of you have your collarbone broken? Any of you in your life? If not, you are really lucky, because I immediately realized that almost for everything you use both your arms. So like it was very, very, very hard, and now I can imagine how hard it might be potentially for people who cannot use both arms for whole life. Anyway, I was able to make it, and here we are to talk a little bit about knowledge graph. Those of you who were here before the lunch, professor did great presentation about data mesh, and he touched knowledge graph a little bit. At the time it was more from perspective of architecture. Here we are going to talk more about it as a technology pattern, and it's going to be a really introductory level. So if any of you already have experience with knowledge graph, with graph itself in data world, most likely you are going to know the things that are going to be said here today. For those who don't know anything about it, I hope it's going to be beneficial. So really technical presentation and introductory level. As you can see, my name is Karol. Lacuska. I work as a solution architect for Takeda within Enterprise Architecture Group. Maybe you know Takeda, maybe not. Takeda is one of 3, 4 biopharma leaders, generally pharma leaders over the globe. Takeda started last year with big IT center here in Bratislava, and we focus to data democratization and generally provide the data for a wide group of people within company to be data-driven company and to make a decision based on the data. Nowadays, many people talk about the data. Many people talk about how to ingest the data, how to process them, how to store them, how to be consuming them, and what to do with them. Efficiency of scaling, efficiency of consumption, all of these things around. And one of the possibilities how to model, how to construct the data models, is to do it via graphs. It's coming from the mathematical concept of the graphs, but it's specifically for the data. And as I said, currently I work for Takeda as a solution architect within the Enterprise Architecture Group. Something about me from my past. Previously I worked as a cloud architect, so for setting up cloud governance, streaming of data, so something what was really close to the data world, security control plane in cloud, so how to handle all security aspects in the cloud, and everything actually what relates to the cloud in terms of how to spread services across several, specifically in AWS, it's about AWS accounts. Networking was mentioned here a little bit. Yeah, it's a bit problematic in the cloud, but manageable. Before that, I was working like a lead engineer, so leading engineering teams for development of the product, which was based on the OpenShift. And in the end, it was like managed container platform as a service. And previously, I'm coming from a Unix and Linux world, so I really like Unix and Linux systems. It doesn't need to be restarted every month when we are in a server world. So that's something about me. And now let's go to what we are going to talk about today. So knowledge graph in data world, what is it? Yeah, why people are talking so much about it, and what's behind it in its terminology and its core. Knowledge graph as everything, as all data that exist in data world and want to be consumed, need to be constructed within some data model or within some model. So we are going to say something also about the knowledge models. Then, as you may be heard, as it is also presented on the page as the name of this presentation. So semantic knowledge graph. Yeah? So we can have a knowledge graph or knowledge model, but the best is to get there also some semantic layer by which we can get more information. So we are going to say something a little bit about what that semantic layer is. And then, okay, so we can have data stored in the graph, or we can have data stored in standard tabular format. It can be row-based, it can be columnar-based, several formats, but tabular format, or graph. So why graph over tabular format? And then hopefully also to mention some use cases. So, what is knowledge graph? What do you think? What are the key concerns or key things that people at any level in all companies think about when they are thinking about the data, other than security, other than, okay, I need to store it somewhere in the beginning, but when it comes to the processing or consumption, what are their key concerns? The key concerns that most of the people have is fast, how fast is the speed, how fast data can be ingested, processed, ready for consumption, how fast I can retrieve the data, but mostly to understand data. So if you have a data in some data model, for example, in tables, you may be struggling with understanding how those data relate together. Each field, each record, what does it really mean? And specifically, what does it mean to some other field, some other record, to other table in data model? And here we are coming to the point of knowledge graph. So because knowledge graph provides semantic network, so network of which represents or connects diverse data together and are described by kind of semantic metadata. So on the right side, you can see simple picture. It's not really it's not really described there as a IT terminology, but it clearly describes some relations. So we do have on the top conference. We know that people that are here are innovation enthusiasts. Some people do some presentations. So this conference hosts these kind of people. This conference is type of tech conference. And these people work in several group of companies. And what is that kind of semantic that we get from that is that these groups and these people are having same interest in innovations, interest in data, interest in cloud, sustainability, whatever. What is the content of this conference? It could be potentially extended by this information. This picture could be potentially extended. So how we call it, that information about same interest, it's inferred facts. So inferred facts are something what we get by having a knowledge graph there and having formal semantics there. And that's actually, we will come to that also later, but that's what is that semantic layer, because as I said, that's something what we get on the top of initial information. As I said, we need to have data stored somewhere, and they need to be stored and connected in particular way. So here we are coming to the point of what types of knowledge models do we have. There are two types of the models. One is property graph, another one is RDF. Or RDF star, as you can see there. RDF star is actually like extension, next iteration of RDF, which came to the scene decades ago. And in the meantime, it was extended to that RDF star, which provides more possibilities. So what's the difference? Property graph is something more simple than RDF because it consists of simple node edge node concept. So someone do something, or something has been done by something else. In manufacturing, for example, something happened with the material. Something happened during the logistics. It can be stored in property graph, and if it's in property graph, it's simply stored in the way of a literal string. So as you can see here, Karol presence on 20th of October, knowledge graph. So the information, the edge or relationship between Karol and knowledge graph is simply literal string, and in the background it's stored as a key value pair. So that's how it's in the end defined in JSON format, and we can be querying it by Cypher, OpenCypher, Gremlin, Path Query, for example. Mostly used, most likely, are Cypher and OpenCypher. OpenCypher is side branch of Cypher, which is more flexible in terms of how fast functionalities for querying are being added there. On the other side, we do have RDF or RDF star. It looks very similar. It consists of subject node, predicate, and object node. So by first look, it's almost the same. Karol presents on 20th of October knowledge graph. Main difference there is that within RDF model, you can store the data, or you can store the relationships, so predicate, also as a separate node. So if you store it as a separate node, you can connect it with anything in that model. Because in property graph, you do have edge or relationship connected to those two nodes. When you do a query, it's going to show you what is connected to particular node, or what is connected to this particular edge, but it's not going to show you a whole data model or everything what can be connected to that relationship. When you do it by RDF model, you can connect to that anything, and that anything, when it's connected to the predicate, is going to be shown when it's queried. And you can also construct it in a way like we can see here. So presence on 20th of October, it can be like two separate nodes. So you can have Karol presence knowledge graph, and as a separate predicate, or that information which is more detailed, is that on 20th of October. That information on 20th of October, you can connect to anything else, what happens on 20th of October. For example, anyone else who was here presented something else, for example. Now, why we need both? So as probably you already realized, RDF star provides more capabilities. So why we need both? Property graph is easier to model. It's not so thick as RDF from perspective of how thick the data model is. So it's easier to define the model, even if it doesn't, if you will come to that, it doesn't have a real schema, it doesn't have a real semantics there, but it still gives you the graph representation of data that are connected. So it's still possible to use it for highly interconnected data, and it's better, if it's enough for your needs, it's better to use it, for example, when read efficiency is important. So when you need fast data traversal, really fast data retrieval. It's also good when you have big or many depths in your in the data that you process. For example, lots, like materials in manufacturing. That's good. That's a great example. So you have a hierarchy there of the lots, parent lot, child, and so on and so on. And if it's enough, if you don't need to build semantic layer there, it's good to build the model based on property graph there, because it's going to be easy and fast to get all required data about those plots. For example, we did it recently in Takeda, and we have a depth of 70 lots. So we needed to be able to get information about potentially all 70 players. Yeah, so on the top I do have a parent child. In the end I have last a parent lot. In the end I do have a child lot, last child lot, and between that I do have 70 layers. And it's really fast and faster to get the data if it's defined within property graph than if it's defined in RDF model. On the other hand, RDF, as we said, it's better if you want to build a semantic layer there. If you want to build a layer which gives you inferred facts, it's needed. Build it within RDF. And it's going to give you much more flexibility for data retrieval, because you can construct the queries in much more ways, how you want to be getting data, how you want to be visualizing data. So RDF model is much thicker than property graph. It's going to give you much more possibilities, but it's harder to define it. Yeah? And it's not so fast for data retrieval when you make a query against the model. On the right side is simple representation of same data and its difference between storing it within property graph model and storing it within RDF graph model. So as you can see, yeah, as I said, that connection is defined there as a separate node, and it can be then connected with anything. Here is another summary, RDF versus property graph model. So what's the difference and some information about it. So the most important from that is property graph doesn't have formal model representation. It doesn't have any schemas. Yeah? It's just simply node, edge, node. On the other hand, RDF has schemas that can be defined there. Schema languages or schemas. This, as you can see, I taken from one side, since it's really great summary. I wouldn't really call it as a schema language, it's schema. And for RDF, it's mostly by RDFS and OW. And these are most common schemas used there. For traversal of data, for querying of data, in RDF, it's about SparkQL. In property graph, as I already said, it's about Cypher, OpenCypher, path query, or here we have a Gcore, GQL. It's not really standardized, depends what you want to use. Yeah, for example, there you can use also Gremlin, what we did. OpenCypher is not able to go, or wasn't able a couple of months ago to go for more than 50 depths. So that's why actually we used in the end Gremlin for data retrieval. Now we are coming to the point of semantic layer, because we said that okay, if we want to get inferred facts from the data, so to connect them in a way that in the end I can use common business term for the data representation, for example, same interest. Yeah, we need to do it in RDF, and then I get a semantic layer. Semantic layer, so here it says something, it's actually business representation of the data, and maps complex data into familiar business terms, as I said. Yeah, so it can be product, it can be same interest, and that interest can be somehow called also in a bit more detailed name. How in the end it's expressed or defined. Yeah, so here we do have example of RDF schema, very, very simple. So semantic layer is expressed by ontology. Ontologies or formal semantics are defined by ontologies. Those formal semantics, it is what gives us information, actually what this data represents, what this data says. And the semantic layer is expressed by ontology. So what we can see on the left side at the bottom, it's ontology connected by RDF as special terms and RDF. So it's RDF as schema. And here we can simply see, what is it? So we do have a group of animals, dog and cats. Dog is a class of animal. Cat is also class of animal, even if it's not really like described there or connected, but it's same. Cat1 is class of cat. Cat2 is potentially also class of cat. And cat2 is hosted in zoo 1. And what is this about? You can see there RDFS range. RDFS range is the property which says that actually animal is hosted in zoo. And that's what is that added value of this, because from the predicate, which is that zoo hosts something, we get information that zoo hosts also not only the cat2, but the animal generally, animals. There is another connection, as you can see there, subclass of. So it says something about hierarchies. So it's subclass of bigger class. Cat is subclass of animal. All these terms like RDF type, RDF as subclass of, RDF as range, and there are many, many more, are coming from the standardization. Particularly here, it's about standardization for RDFS. And it's, as we can see here, it's driven by W3C working groups and their standardization processes and protocols there. Okay, now we know what is generally knowledge graph about. We know what is semantic layer, what we can get by that. But now people may ask, okay, so like same I can get from tabular format as well. Well, yes, but not so easily, I would say. So here we have simple summary why it's better to use graph instead of tabular format. Of course, not for all cases, but in my opinion, for most of them. Better performance. So as I said at the beginning, one of the key things that people want to get that when they work with the data is to get them processed and retrieved fast. As we verified by our proof of concept that we did with property graph model, and by the way, we did also it with RDF or another business case, but now we will talk more about the property graph. It's much faster to process a lot of the data and to retrieve all of the data that are highly interconnected, so you have a huge amount of relationships between those data when you do it within the graph concept as when you do it within the tabular concept. Easier scalability, So especially, again, for highly interconnected data, if you want to add new data and to cover all relations that new element has, it's most of the time really, really hard to define it, to understand how and where it needs to be put within the model and within the tables that are from which data model is constructed. Here, when you do it via graph approach, it's easier. Of course, you still need to understand what the data model is about, how data are defined there. But then once you understood this and it's easier to understand it, you simply just add it as a next node by particular relationship to some other node, and that's it. You don't need to go through all those tables and all records in the tables within particular data model. If you define knowledge graph within RDF, it gives you possibility to get or define their semantic layer and to construct it in way of formal semantics defined there. So that's what gives you additional layer for understanding of data relationships, that semantic layer, inferred fact. Yeah, so something what then like you can use graph search or semantic search based on those standard business terms like product or same interest, and so on and so on. Relationship between data entities are understandable to both. Yeah, so not only for some applications because they are queries, but also for people. When they are looking to that, it's much easier to understand. Okay, so I do have presenter which does something. I do have one data asset for which someone is responsible, who owns it, what is the content of the data asset, so exactly data catalog, right? So this is much easier with knowledge graph than with tabular format. And as I said, relationships can have attributes as well. So for example, Karol represents knowledge graph. Relationship is that Karol represents, I present something. And another attribute is that I present it today on 20th of October. Some numbers about the performance. So I said that it's much faster, even for large data sets, and actually, especially for large data sets, it's much faster. So these are the data from what we did, and as you can see there, or step back. When you want to put the data into graph, into property graph model, you need to get them structured into CSVs. One for nodes property, another one for heirs property. So that's what you need to do as first. Okay, it's an additional step, but it's actually very easy to do it by Python, for example. As you can see, we processed in the end 46.2 million of records. So big amount of data, right? To get it from initial tabular format before its transformation, data transformation or business transformation of data, into that CSV, two CSVs, it has taken less than 1 minute. So very easy, very simple. Then what do you want to do? You want to do that business transformation of data. So actually you got it in some form at the beginning, and now you want to put it into knowledge graph in particular way. That's what you do with data, the business transformation. For this amount of data, in terms of all records, 46 millions, in terms of rows, number of rows which you can see there, it has taken to get it into Neptune database. We use a Neptune in Amazon, in AWS environment. It has taken 5 minutes for edges, since edges are in bigger size, in bigger amount. So in total, it has taken 7 minutes to get data transferred from its raw or that semi-structured format into the final state. 46 millions of records in 7 minutes. Of course, for particular data transformation, it may vary based on the complexity of transformation that you need to do. We did it for lot, track and trace, so actually tracking the lots which I mentioned earlier. So 70 depths and these things. At the bottom, we can see another stat which show us data retrieval. Yeah, because on the top we can see data ingestion or that initial data transformation and business transformation, which was also about data ingestion into graph database. At the bottom we can see numbers for data retrieval. So data retrieval for example, you want to get information about 500 of nodes. You write particular query, and it has taken 11 seconds to get all information that are there for those nodes that you requested to be visualized or queried. Really, really fast. Just one more thing to the transformation, which I mentioned in regards to the table on the top. This, when is this being done in a tabular way, it's taking approximately 40 minutes. After many refactoring of the code, getting it getting it done faster, we got it from more than 1 hour into 40 minutes. Yeah, here we can do it in 7 minutes. It's something absolutely different. Another thing which you can see there is that in the end, data representation, when you get the data, can be defined in paths and trees. It's just how our data represented in the end. So paths are more verbose than trees, and also data retrieval for getting in the path is much faster. Yeah, for example, for 10 nodes, it's about 0.5 second. For trees, it's 8 seconds. It's because how it's written in that tree. Yeah? For path, you get several separate JSONs. For tree, you get only one JSON. And into the JSON, everything needs to be written, which represents the data then, and it gets more time to construct it. For most of the cases, it's better to get data represented in way of paths. So here we can say something about graph use cases. Yeah, so okay, we do know that it's faster. We do know that it's easier to scale it. We know what is it about. We know why it might be good to define semantic layer, or where can be better to define it within property graph model. But actually, what are real use cases? Yeah, so just a couple of 3, 4 or 5, 6 written here. So for example, manufacturing. Manufacturing I already mentioned. Yeah, so you have many materials that are somehow used in the manufacturing, and next cycle or next life of the material is dependent on the previous life of that particular material or on some other material. So you want to track the life cycle of the material and its dependency. So that's one great use case. We exactly did it, what you can see also in the stats of property graph. Supply chain. So for example, supply chain optimization, route optimization, risk identification. So you want to know what is the best or most effective way of delivering something. Yeah, shortest or fastest path. So if you get data represented in a way that, okay, I can simply realize what is connected to what. Yeah, so factory to warehouse to some company which then picks it up and deliver to something else. Then next step of that, for example, from car to the ship and so on, I can easier say what's more efficient. Similarly, it's for risk identification. So if I want to know, okay, if now people are going to be sick and are not going to be picking up it from the warehouse and by car delivering it to something, or same for the ship, what is going to mean there for my case? So it's much easier to get this information and to do analytics, further analytics behind it when you get the data defined from the graph. Yeah. In financial industry or 360 views of customers and products, so we want to understand everything about your product. What people say on that, on social networks, how that product was being sold, what price, when, and so on and so on. You can combine structured and unstructured data and then do some transformation and having it in a knowledge graph then. it can be potentially enhanced by some NLP and algorithms there, for example, especially in financial industry when you want to do some fraud detection. Yeah, again, because of same reason. And especially for the data that are really connected to many other elements. Yeah. So exactly this kind of investigations when, like fraud detection, for example. And last two for now, data catalog and data lineage. So that's one or two great examples, and I think it's something what anyone who works with data can imagine. Because, as I said also at the beginning, people who work with data want to understand the data, how they are connected. And how they are connected means, okay, so what these data are about. So some kind of metadata about the data. What this data really means. Even if you see that, okay, one element is connected to another by some relationship, you want to know what that element node means, really. So for that, it's good, and especially in big companies, it's absolutely necessary to have a data catalog. Also, for example, if you want to have a really working data mesh, which was mentioned today also, and it's really known term these days, you want to have a data catalog, because data mesh without data catalog doesn't have a sense. So it's great to use it there. There will be some visualization of it a bit later. Same for data lineage. So we want to understand what happens with data. Yeah. So where does data come from? What happens with them? And where does data go? So something a little bit more specific about data lineage. Yeah. So for better imagination. So you have some attribute which can be particular record or field as a field or table. In one application, you get it into application 2. So you can imagine it like, for example, I don't know, in SAP, you have something in SAP ECC. Then you get it into some other component within SAP environment, for example, Data Warehouse Cloud. And it's still same attribute. You do it because of some other reasons, like, okay, Data Warehouse Cloud, you provide it also for some other usage, you do some further analytics there with that, someone else do it. So that's the reason why you get it there. But it's still same attribute. But you want to have this information somewhere, that this is something what happens in your environment. And actually what exactly happens with that attribute. Here, almost nothing. Yeah, it just got from application 1 to application 2. Then something happens within application 3. It's another attribute, another data. And what happens is that attribute 2 from application 3, we get into some data lake, for example, which is actually application 4. Same we do with that attribute 1 from application 2. We get it into some data lake where we combine the data. So attribute 1 with attribute 2 into attribute 3, kind of the end data model, let's say, for simplicity. Yeah? And all this information we want to have stored somewhere to be able to say, okay, so if something happens with attribute 2, I am not able to get attribute 3. Or if something happens with transformation or replication of attribute 2, I am not able to get attribute 3. So that's why data lineage, information of data lineage are needed. Why to do it in graph format? Again, it's a huge number of relationships. If you do it for 50 systems, more than 50 systems, source systems, and you have many attributes, many tables there, you get it into some data lake, and then you combine it. It's a huge amount of data, huge amount of relationships. What is going to happen when something failed during the replication or transformation? So here we are coming to the complexity of storing and scaling, as was said before, and also traversal of this data is much easier and it's much faster because of the thing that I mentioned earlier. Similarly, for data catalog. So as I said, data catalog is something what is absolutely necessary for big companies that do many integrations and for companies that want to have a data mesh. Here you can see simple description how part of data catalog can look like. So John Brambo is data steward for data asset. So his role is data steward as the type. He is responsible for data asset X. Part of the data asset X, or class actually, that dashed line means it's class. And in this case, table is class of data asset X. Column is part of the table. Data type is defined there as a data type, in particular column, and similarly for datetime. Yeah, so datetime is data type within the sales data, which is the record within stock movements, what is actually the name of the table. So very simple representation of data catalog or part of the data catalog. Now imagine, yeah, you have this. You have it in much more bigger scale because of your company, which is big. You need to do it for thousands of data assets, yeah, for hundreds of the rows and all information about those tables, for example, columns, data types, and so on and so on. You want to add something new. If you do it by tabular format, it's going to be nightmare. It's going to be really almost impossible to get it defined because it's about one-to-many relationships for each element which is being added there. If you do it by knowledge graph, you can avoid those unnecessary needs of joins which you need to make when you want to get end information. And also, if you are at really big scale, you might come to the point that you are not able to do it, and you must create like small silo, so small separate data catalog for something, yeah? And you want to avoid it because then you need to maintain more data catalogs. So these two use cases, for example, a little bit more described. That's it, I would say. So thank you very much for your attention. And now we do have some questions. So is it possible to convert SQL from data whole database to knowledge graph? Yes, it is. Not sure what you mean, like whole database. Like, yes, of course, it is possible. You need to do, if you do it into a property graph, you need to get it into separate CSVs, and then you, by knowing what you actually want to represent in that in the knowledge graph or graph database, you do conversion into property graph. But yes, if you want to do like in more detail, please specify and we can discuss it. Can you detail a real knowledge graph use case from your org's domain other than the textbook case? Okay, so I mentioned supply chain, yeah? I mentioned manufacturing. So manufacturing is about those lots. You want to know life cycle of the lots, parent, child, next child, next child, next child. Yeah, because you want to know, okay, if I need to use child lot 36 for my product, what it comes from, what, for example, was the time when I got it produced, and you get it from the information of the child, which is about that, from information of the lot, which is about that particular child lot. Another one was supply chain, route optimization, risk assessment, about then data catalog, data lineage, fraud detection in financial industry. Can property graphs be used to mimic advantages introduced by RDFs, e.g. at the predicate as middle node between the two original nodes? At the predicate as middle node? Yes, it is. Yes, it can be. I think I described it previously. Anything else to be voiced? If not, then again, thank you very much. And if you are going to have any additional questions, I'm going to be at Takeda point in main tent, so you can catch me there.